let's get started. My name is Morten Rasmussen. I'm an engineer at ARM. I'm the lead developer on energy-aware scheduling. I'm going to talk a bit about what we're doing trying to get the EAS upstream in this presentation. Well, it is a presentation, but if you have any questions, please ask. I'm here to try to have a discussion about what we're doing and hopefully make it more clear what we're trying to do, trying to get EAS upstream. So I'm going to spend first 3 slides just trying to describe what EAS is about. I wasn't really sure what the audience would be today. Some of you might know EAS in detail already. Some of you might be new to EAS. Some of you might be considering actually spending time looking into it. So I want to spend just 3 slides just describing what it is. So the basic idea is that to take most advantage of all the vast power management features we have in modern SOCs, we need to improve Linux. We basically need to introduce energy awareness. The problem we really have is that we have a variety of system topologies, big.LITTLE systems, different power stage frequency domains, lots of advanced features, and we have some workloads. And depending on how we schedule these workloads, we might get different power and performance numbers out of it, and it's quite hard to tune these things. So what we're trying to achieve with energy awareness is to make the OS aware of the choices it makes when it comes to task scheduling, because where you place the task will actually affect what OPPs you might end up selecting, because if you put a big task on the CPU, you might want to increase the frequency. That might have knock-on effects on other CPUs and other tasks. And also, which CPUs you choose to wake up will have an effect on which idle state you can select. So actually getting the task scheduling right is actually quite important to get your power and performance numbers where you want to have them. So the bit I'm going to talk about, and the bit that's really what we consider the core EAS part, is actually the task scheduling itself, the scheduler modifications. Now, energy-aware scheduling affects a lot of other things, like the CPU idle framework and frequency selection. I'm not going to talk so much about that today. I'm going to focus on the task scheduling and the patches we have in flight that try to improve that. Come on. So what is this energy-aware task scheduling? It is really about trying to put tasks on CPUs where it has the least energy impact. We want to get as much out of our battery as possible, but at the same time get a reasonable performance. We don't want to constrain tasks in terms of compute resources. We don't want to slow them down deliberately. We want to give them the performance they need, but we want to place tasks intelligently to try to minimize the energy consumption. I have an example here on the right. It's a made-up big.LITTLE system. We have 4 CPUs, we have 2 littles, 2 bigs. We have some tasks already running on some of the CPUs. We have one which is currently idle. We have the little cluster at one OPP, we have the big cluster on another OPP, and then we have another task showing up. And now the question is, where do we put this task? If we just look at the mainline scheduler as it is today, it is most likely to put it on CPU 3 because it's idle. It's the safe choice. It's got nothing else to do. Then from a performance point of view, let's just put it here because you can't get any better than that, so you can just go with that. But if you care about energy for your system, that might not be the optimum choice, because maybe if we stuck it in here instead, we could get almost the same performance, or the same performance, but we could actually leave this big CPU powered off. And that might save power. But we're not really sure if it saves power or not, because it really depends on the implementation of the particular platform. So that's why we really need a better description of what kind of platform are we running on. And that's where the idea came in. Why don't we have a model that basically expresses all the power states, all the OPPs you have on the platform, have power numbers for each of them. So we really need, what is the trade-off between putting a task on one CPU where it might actually cause the frequency to increase, or put it on another CPU that might be idle that you have to wake up. I mean, that trade-off is platform specific, so we can't really make any sensible choice without knowing more about the platform. So that's why we need an energy model. The other thing we need to do energy-aware scheduling is that we need to have some idea about the load or the utilization caused by a task. So we need the scheduler to track each task with some accuracy to tell us, is this a demanding task or is this a tiny task that we can easily fit in along with other tasks on the same CPU? And for that, we need something called utilization tracking. It's based on this PELD algorithm that you've probably heard about. It's in the mainline scheduler already. We use it heavily for energy-aware scheduling. And the utilization is sort of the input to our model. We get utilization sort of describes our workload scenario right now, and then we combine that with the energy model to figure out what is the cost of doing various scheduling decisions. And the nice thing about the solution is that if we have a model of the platform which is generic enough to capture all kinds of platforms, then the whole thing should just work. I mean, if we make decisions based on the model, we come up with potential decisions, and then we just query the model and say which one will give us the least energy impact, and then we choose that. Then we should be able to support any kind of system, big.LITTLE, SMP, whatever you can come up with in terms of frequency domains, power states, it should work. The model itself is really, really simple, and it has to be simple because the model lives in the scheduler, it lives in some of the most performance-critical code paths in the kernel. So we can't go off and do something which is really complicated, requires a lot of math, because it will hurt our performance if we spend too much time computing what is the best choice. So what we're doing is that we have a really, really simple model. We basically just take how much time are we busy, how much time are we idle, and then we have our model of energy data for our platform that tells us, okay, we spend X amount of watts in busy and Y amount of watts in idle, and we just sum it up, and that way we can get a rough estimate of the energy consumption. So basically the way it works in the kernel code for energy-aware scheduling is we come up with potential choices when we have a new task showing up. And when we have two choices, then we compute, using the energy model, what would be the energy outcome of the two choices, and we pick the one with the least energy impact. So yeah, as I said before, there are basically two inputs. Utilization characterizes the current task, and we have the platform data provided and describing the platform. And combining those, you can come up with the energy estimate. Question?
Is the decision only considered a new task, or it can reschedule all tasks?
So we don't just consider new tasks. We use that as an example because that's fairly easy to describe. Right now, well, for energy-aware scheduling, it's about trying to give you the same performance but save energy. If you have a workload which fully utilizes your system, we can't really do anything because we want to give you all the performance you need, and if you need the whole system, we can't save any energy. So what we're focusing on is those mixed load scenarios where you have some spare capacity. When there is spare capacity in the system, I mean idle cycle somewhere, it means that we have some room to shuffle around tasks and try to save energy. And when you have that, then it means that some tasks will eventually sleep, otherwise you wouldn't have spare cycles. And that means that those tasks will come through the wake-up path and actually be considered new tasks, or at least waking tasks. So a lot of our focus in the energy-aware scheduling patch set is actually on the wake-up path. Our intention is to also use this information for balancing across all CPUs and some of the currently runnable tasks. We don't do that in the patch set right now, To a great extent, we do a bit of balancing, but we could probably do more, but I can describe in more detail what it means. But you can consider all kinds of scenarios. I mean, the model is not restricted. You can use it to evaluate any balancing decision you want to do. What I'm saying is just that we don't apply it everywhere right now because for some scenarios it doesn't make sense. Like if you have all your CPUs running flat out, it doesn't really make sense to query the model because you know you need everything anyway. Does that answer your question?
So what you're saying, you don't do migration, right?
Sorry again?
You don't migrate a live task to another.
So the question is, do we migrate a running task? We actually do and don't. In the upstream patches, the ones that are posted on the list, we don't move currently running tasks. We need to do that for big.LITTLE systems for one reason, and that is if you have a big task that for some reason starts running on a little CPU, it would normally stay there forever. But for big.LITTLE system, we might want to migrate that to a big CPU. So we do have a few extra patches that gives us that behavior. Now, implementing that behavior in an upstream-friendly way requires us to change a lot of code, or at least re-express it. So right now we have some simpler patches that work around that problem, but we want to do it the right way and post the upstream-friendly solution. No, well, the mainline scheduler is assuming that everything is a nice SMP system. You don't have frequency scaling. You don't have things like big.LITTLE. So we need to introduce awareness of the different compute capacities.
It's the migration part you say is the hardest.
So the migration is not impeded in any way by EAS. Migrations will continue. It's just that the lookup of the energy model is not done. That migration time is upstream instead.
Yeah.
Having said that, all of the evaluation that's happened so far with EAS leads us to think that just optimizing the task breakup pathway is giving us most of the benefit anyway. Sure.
That particular use case we can
Just so you know, if we answer your question, if you have a microphone, we have a hard time.
Just keep it here for the next one. Okay. More questions? Okay, I'll continue then. So that was just an introduction to what EAS is. So we've been talking about this EAS thing for quite a while, actually. You can see on the timeline here that we actually go back to 2013 when we did some of the first postings and we got our first maintainer feedback. And there's been quite a few things going on in the meantime. Well, this slide is not displaying properly for some reason. We've posted a number of RFC patch sets, which we're trying to capture our idea, prototype what we wanted to do with energy-aware scheduling. And there's been other modifications and patches going in. Linaro produced patches to actually start looking at idle states and at task wake up to try to do more intelligent selection of the CPU that would be woken up to run waking tasks, already merged a long time ago. There's work going on SCED-DVFS. We did some improvement patches for improving the PEL utilization. Some of them already went in. We posted patches that tried to introduce new ways of tuning the system behavior. There's a whole lot of patches. Down here on this blurb that doesn't show anything, I think it says LISA tooling, which is tools to help analyze scheduling. And ARM has been working hard on that for a long time. And we have this whole wonderful analysis toolkit, and there is going to be a session about it, and it should actually say here, I think it's tomorrow at 4 o'clock, 10 past 4.
And it's Secretariat 1 room.
In Secretariat 1,
Room.
yes, 4:10 p.m. tomorrow, and I think it should be in Pathable somewhere.
Yeah, normally we have send all the description on the festival. There is a pro management group discussion.
Okay,
Just be aware that that's a 2-hour session. It's going to go through like a training-oriented description of the tool. So it's a 2-hour thing, just so you know.
Yep. So our strategy up until now for upstreaming EAS has been that it's really complex what we have set out to do. We want to combine frameworks in the Linux kernel that haven't been talking to each other before. We have CPU Freak, we have CPU idle, we have the scheduler. They all had their own independent policies and did their own little thing, but actually to get where we want to be, they have to work together. So we need to work across frameworks, which is a complex thing because it's different maintainers that have different views of how things would work. So to start with, our plan was, or the way we did it was that we wanted to prototype the whole thing so people could get an idea about what are these crazy people talking about? Where do we want to go with this? Because they are rambling about combining stuff, but we need to see some code to see where they're going. So up until RFC-v5, the posting we did on LKML, we were building up this story. We tagged it with RFC because it was a prototype just to show where we're going. And we posted it as a whole thing so people could see the full picture. We were well aware that as the patch set grew larger, it was not going to be merged in one go. It was there to provide the story. As we reached RFC-v5, sorry, I would like to add there as well, as the other reason, there's sort of two reasons for having this massive patch set. One was to see the full story. The other one was to have a prototype that we could actually run on real platforms and see how it behaves, get some confidence in that the whole thing actually works. So we could take it, work with partners on real silicon, validate that it actually works, because it's a big thing. I mean, we can spend a long time upstreaming this, so we need to be fairly sure that it's actually something that's going to work in the end. So when we got to RFC-v5, we had a full stack with most of the features in there. I'm not saying it's complete. There are still some bits and pieces that needs fixing, but at least we got the overall behavior we want. And it's been validated on a number of platforms. So now our focus for our upstreaming effort is changing. We're not going to focus on creating even more and bigger consolidated patches. We know that it's working. We have some confidence in the patch set. So what we're going to do now is that we're going to split it out. We have already done that for some features. Sched Freak was originally posted as part of these RFC patch sets. There's no reason to do that anymore. It's got its own life now and lots of attention and being reviewed separately. We're going to do that with all the bits and pieces we have in this prototype, take each feature out, mature it, post it so it can be reviewed separately so we can have focused in-depth reviews of each feature, and hopefully that way we can also parallelize the upstreaming process because not all features depend on each other, so we can have some of the review discussions in parallel. So the things that are in progress right now, as I said, is Sched Freak or Sched Util or whatever name it has now. It changes every day, I think. We have some bits around scheduler tuning. I think some of them have been posted already. There are more bits to come. And we need some fixes for the utilization signals. Some of them are in the works. We know there are problems around task groups, no hertz. There are small fixes and stuff that needs to go in. But while we're progressing all these things in parallel, we still want to maintain an integrated branch. So if you want to evaluate the full thing, you can go in a single place and check out a branch and look at it. But it doesn't mean that we're going to post consolidated patches going forward. If you want to see the full story, then you have to go to linuxarm.org and take the latest branch. So, just to go into a little bit more detail, I wanted to show you the patch stack. I don't expect you to read all the titles of all these patches, but these are actually all the patches that are in the latest integration branch we have on linuxarm.org. And you can sort of split those into to subsets, each implementing different features. So at the head of the patch set, that's actually the bottom here, and this is the last patch in the patch set. And going upwards, we have a number of features. And going up until this point here, which is about 2/3 up the patch set, this is where we have implemented the actual scheduler modifications to do energy-aware task scheduling. The top bits are to do with, the last bits here are to do with thermal integration, making the scheduler aware of the fact that sometimes CPUs might be constrained in what OPPs they can select. And the final bit up here is actually SCED-free, but as I said already, that's got its own life outside of this patch set already. So up until the point where, and including where we introduced the task scheduling features, that we consider as the core task scheduling bit. That's what we mean when we say EAS core. I mean, EAS is a lot more than just this, but the task scheduling bit is actually up until here. So if we go through all these subsets, how many have I put here? There are 6 parts. The first bit is quite simple. It just gives us the basic ARM implementation of frequency invariant utilization tracking. As I said earlier, it's all about having an accurate view of your workload. And to have that, we need some support from the architecture. We need to make sure that the utilization signal we have for each task can actually cope with the fact that CPUs might run faster or slower because of frequency scaling, or the task might migrate between big and little CPUs. So these patches we have here at the beginning are actually fairly simple and can go out separately. So the plan is to post those separately. We have a few different implementations here because it has to hook in with CPU Frig, because CPU Frig takes care of the frequency scaling. But that is one set of patches that we're going to split out and post separately. The next set introduces basic capacity awareness. That is basically a set of patches that changes a few things in the scheduler, so it actually knows that there can be a difference between CPUs. You can have big or little CPUs. It doesn't use the energy model, and I think most of those changes should be fairly non-controversial. I mean, this is the basic, the absolute minimum you need to get big.LITTLE support upstream. We don't talk about energy-aware scheduling on big.LITTLE system, we're just talking about getting consistent performance. Because today, because the mainline scheduler doesn't know about the difference of CPUs, your task can run anywhere. So if you just take mainline, you don't really know what you're getting. It might run fast, might run slow, it all depends. So if we take these patches, that should fix that problem. We're actually currently working on re-expressing those a little bit and trying to massage them better into the upstream code. Some of the code have changed not too long ago, so we're working on a better way of expressing this. The third bit.
Hey, Morten, can you comment on, you say the real time and deadline doesn't matter?
So the other problem there is, in addition to being able to handle big.LITTLE systems where you have different compute capacities, if you have a substantial load caused by RT and deadline tasks, it's actually not considered today in the wake-up path. When you wake up a task, it actually just looks for its CPU, which is idle right now. It doesn't know if the CPU you're putting this task on might actually be busy 50% of the time due to RT tasks. Because right now, the wake-up path doesn't look at capacity of the CPU at all. It just looks for an idle CPU. So we want to change that so the wake-up path actually considers what is the capacity of the CPU, how much spare capacity does it have? Because to me, it makes more sense to actually look for the CPU with most spare capacity if you wake up a new task, or at least for a CPU with sufficient spare capacity to handle that additional task. If you do that, then you should get your big.LITTLE placement right. And if you have RT eating away some of your capacity, then you would avoid those CPUs as well. But it's not there today, so if we fix this, we would fix both big.LITTLE and RT and deadline pressure. So, did I skip one? There's one, okay. So the third subset of patches is actually just infrastructure patches to set up all the data structures needed to store all the energy model data. So the table information we have about the power numbers for the platform, we need to make them available to the scheduler. So there is some code in there that attaches a new data structure to, we have something called the sched domain hierarchy inside the scheduler, which sort of expresses the system topology. So we hang off a bit of extra information in there with the tables of power and performance numbers for each CPU and things like that. So this is pure infrastructure. It doesn't provide any functionality. It doesn't really depend on anything. I mean, if you merge that, it would be dead code today, but it wouldn't harm, I think. So we think that can be posted separately as well. The fourth subset actually introduces energy model data. Right now, in the integration branch, we have hard-coded this information into the kernel, which is, of course, not the final solution. So we have tables for TC2 and for Juno, but those data have to come from somewhere else. I mean, it can't be hard-coded. And currently, there is a discussion about where should this information come from. Some people think it should come from DT in one way or the other. Some people think it should be probed dynamically, maybe combined with information from DT. A third option would be let user space set it, have some sysfs entries where you can override it from user space. It's not really clear where we're going because the sorry, question?
User space helpers.
Sorry?
User space helpers.
So when I mean user space, I mean just exposing some sysfs entries where you could write the table data and tell the kernel about what is this platform you're running on.
Actually, a kernel can call a user space helper.
I'm sorry.
So if I understand you correctly, what you're saying is that you can delegate the problem to some sort of user space monitor, daemon, some service. Sure. So what Martin was saying is that one way of facilitating that is to make it possible for the energy model to be sort of like injected from user space using some API.
Yeah.
Right. So by the way, this is a very, very loaded topic and it's extremely polarizing, just so you know. There are people who feel very strongly about opening this up to user space. There are others who feel that there is no other way, right? So we have a session on this, which is a discussion at 6
There is discussion
today.
at 6 o'clock today, I think, about this. So I think we've done pretty much full circle at least once on this topic. Yeah, I don't know what the best solution is, but actually I have a slide trying to describe the whole problem. So we need our energy model data. We need to use it in the scheduler. So I've drawn this line here because in my world, there are two parts of this story. There is the scheduler side of the story. We need information to make our scheduling decisions. We attach it to the sched domain hierarchy, and then we can do magic in our scheduling. But this data has to come from somewhere. So right now we have an interface where the scheduler takes in these tables, and it is literally just tables with entries in them. Where those tables are coming from, that's the question. And I think the solution lives in the Arch code somehow. So right now the Arch code have to deliver these tables. Now how it comes up with these tables is the big question, because yeah, we have some measurements that we did on our platform. We have a power performance curve, and that's basically what's in this table. But how we encode that in a way and deliver it to the architecture code so it can generate this table is the big question. You can either just have the table directly in DT. You may be able to express this curve using fewer parameters, and then you have some code in the kernel that can actually generate the tables based on those parameters. You might have some dynamic profiling, which at boot time tries to figure out what are the compute capacities at each OPP, combine that with a few power parameters, and then generate the tables. Or you can have some user space helper that can write it into the kernel using sysfs. from a scheduler point of view, we don't really have to worry as long as we get these tables from somewhere. So it's not that our scheduler work is blocking on this. I think the discussions can progress in parallel. How we end up doing it for ARM, I think is a separate discussion. As long as we can agree that we just need some tables that we can give to the scheduler, then the scheduler side of it can progress separately. So, next subset of patches. So this is the middle set of the patch set. So here we have the core scheduler patches, the ones that actually make use of the energy model data to calculate what is the energy consumption, and the patches that hook into the wake-up path and try to evaluate which is the better choice when we wake up a new task and things like that. So this patch set, of course, depends on the availability of an energy model. So those patches will depend on a solution, or at least the patches that provide the data structures to hold the energy information. And if you want to evaluate them, then you need your utilization patches, the ones at the beginning, to be in place. And you also need a way of providing the energy model data into the kernel. So this set of patches actually have some dependencies. But with this set of patches, we sort of have all the core bits we need for EAS core. So the last two bits we have is patches to do with capping of capacity that might be due to thermal limitations, or it can be imposed by user space for some reason. These patches actually depend on the patches that introduce capacity awareness in the scheduler, because if the scheduler isn't aware that the capacity might change, then if we just change it, it might not really have any effect. So there is more discussion about things like this related to thermal management, IPA, in a discussion later today, 2 p.m. I think. It's led by Puneet. And I think it's scheduled to be in Secretariat 2. Is it not 2? Does it show up in Pathable correctly?
3 p.m. 2 p.m. is the hacking session for EAS and IPA. Oh yes, no, you're right.
Okay. 2 p.m. today, Secretariat 2, hacking session about EAS and IPA. And the last bit of the patch set is the Sched Freak, which I said has got its own live now, and it already been covered in a session by Steve Muckle on Monday, and there's also been a hacking session on that already. So, but that set of patches is not the full story. There are more bits that we're working on, especially around the PEL utilization signals. As I said, we know there are some problems. We're working on fixing those. It's really crucial that we have good estimates of the workload. I mean, if we have poor input into our model, and decisions we make based on that, then we will make poor decisions. So we know that there are issues that are even there in mainline and will affect the Sched Freak, but we're also working on various ways of tuning them. So Patrick is working on improving responsiveness on these signals. That all ties in with the whole discussion about window-based utilization and all that. So that's an alternative way of fixing that problem. We want to make better use of PEL utilization and load in the normal load balancing code. In mainline today, we're sort of halfway there. PEL utilization is introduced, but it's not really used, at least not to its full potential everywhere in the load balancing code in the scheduler. We want to fix that. There is some work going on providing tuning. There is the Sched Tune work also by Patrick. Is there going to be a session or a discussion about that? At 3 p.m. there's going to be a hacking session around Sched Tune. And on top of that, we're also working on how to address better user experience. For people that want to use this for product, well, everybody wants. One concern is that the interactive governor that's used in Android, it gets inputs from other parts of the software stack, providing hints about when there is a touch and things like that. We want to try to see if we can somehow make that a part of SketTune or SketFreak, so we can get similar behavior in an upstream-friendly way. So if we can capture that behavior in this, we want to do that.
So we can still support touch boost in an interaction boost.
Yeah, the plan is to see if we can find a way to somehow plumb in the feedback we get from the higher levels in the software stack into SketTune.
So today you don't have that in the current code base,
Okay.
but you have the building blocks to give you exactly that without relying on the interactive governor.
Okay. You
So-
don't have it from but the infrastructure is there, so we can enable it, right?
Yeah.
Okay.
Yeah, I mean, there's of course a lot of cautious evaluation required before you can reach a point where you're competitive with the interactive governor, of course. But our aim has always been to come up with some building blocks that get you there. So, yeah.
Okay.
Okay. So the next steps from here, as I already said, we think we're at a point now where we can split up the patch set and progress things in parallel, have them reviewed in depth, and have separate discussion about all the bits and pieces that we need. What we also want to do is that we want to clean up the existing code. So one of the problems we have with upstreaming EAS is that we're proposing changes to the scheduler. A lot of people worry about the performance of the scheduler. If we touch anything, we have to prove that it doesn't regress. And the problem we have is that certain part of the scheduler code is actually quite old. Some of it might be 8, 9 years old, and substantial changes have happened in the meantime. So there are bits and pieces in there, interesting heuristics that nobody really understands anymore. So we need to get rid of those, or at least understand how they work, because if we build on top of something which we don't understand, we can't really say that we don't harm anyone. And also because of these weird heuristics, it's really hard to fit our modifications in there and be sure that they work the way we want and we don't mess up the existing code. So there is a lot of work in there to work with the maintainer on identifying bits that we can get rid of, because I think there is a lot of code in there which doesn't really make sense anymore. And while we're doing that, we want to, of course, continuously have this integration branch available on linuxarm.org for all our upstream work. And in parallel with that, there is also an LSK branch for evaluation on partner and member platforms. So right now there is a backport to 3.18 for those that are interested in that, and I know there is a 4.4 branch currently being worked on. So in terms of plans for what we're doing next, we're working on an updated patch set. Right now we call it RCV6. We might post it as a whole thing, we might not. We will at least put it on linuxarm.org. I can say that the changes that we're working on right now is we've got a lot of feedback from RCV5. We're rolling that in. We're going to rework the wake-up path, try to make it more upstream friendly. We're going to split that out and post it separately. I think it might be a two-stage thing where we do capacity awareness first, because it doesn't depend on the model and should therefore be fairly easy to, or at least easier to discuss and hopefully get merged. And then we're going to do the energy aware part after that. And the other thing that we're going to address in the next thing that we're going to do is to have better SMP support. So we haven't really evaluated a lot on SMP platforms so far, but we have done some good work with Leo from Linaro on the high keyboard. So we now have a testing platform where we can actually evaluate EAS on an ARM SMP system. So we have some patches for that that's going in soon as well. So on this slide, I want to come back to a question that we're being asked quite often, and that is, you've been working on this for quite a while, so why isn't it merged yet? And as I've said already, it's complex what we're trying to do. We're trying to combine a lot of things, and we need some certainty on where we're going. It's taken a long time to develop all the features we need, and we have a prototype now. Now is the time to re-express all the parts of that and get it upstream. But having a prototype doesn't mean we have something that is mergeable right away. We'll probably have to rewrite each subset of all those patches a number of times before it gets in. But now we at least know that it works. So the big work ahead of us is to re-express all our patches in an upstream friendly way, or have in-depth reviews of all the bits and pieces and get the ACK from the maintainer to say whether or not this expression is okay for being merged. We've spent a lot of time talking about this. We have been talking about this at LPC for the past, 3 or 4 years. So we've really put in a lot of effort in trying to build a community around this. It's not massive if you look on the list. I think most of the participants are either ARM or Linaro people. But we actually know that there is a larger community. There are more members and partners that are actually interested in this. They're just not visible on the list. And we are actually hoping that some of them will come out, because if they show up on the list, we can demonstrate that there is a greater demand for EAS. And that's what we think will help getting this in. If we can have people showing up and say, this actually matters to our products and it actually works for us, I think it would be a great help. The other challenge we have is that we have to prove that this works. And proving that this whole story actually gives you a benefit is quite difficult. I mean, we need a platform where everything works. We need to have power management in place. We need the full software stack, and we need to be able to measure power or energy consumption of the platform. And those are not easy things to get all in one platform. And that's a constant thing that we're fighting. So those are the challenges. I know it's the same for the Linaro Power Management Working Group. They have also been looking for a good platform that would give us everything we need to do power management for a long time. Yeah, that's really what I wanted to say about that, I think. So if you want to help us, come out, discuss it on the public mailing list if you can. It helps showing that there is a community around EAS. It's not just a few people from ARM and Linaro that talk about the same thing every year. It's actually something that people care about. And help us test and validate that it works. I mean, the more platforms we can have that actually try this code out, the better. I mean, there are bits and pieces we don't see when we run it on the ARM development platforms, because they are somewhat different from the silicon that partners are using. So it's really important that we get this tested. And please provide us feedback. If you can do it in public, it's fine. If you're not comfortable doing that, then we have a smaller forum on the EAS dev mailing list, which is still public, but I think it's only partners and ARM and Linaro people that subscribe to that. So if you have any questions that you don't want to post on LKML, you can do it there. Yeah, tell us about your experience with the EAS. And I think that's it. So if you have any questions, please ask. Oh, many questions. So where's the microphone?
This one should be quite quick. You mentioned RFC v6.
Yes.
And a certain indecision about whether to post it as a consolidated set or not.
Yep.
It would really help to have something public to name the set. So I'd be interested in what's kind of countering against posting it, because simply posting it, the name alone is a good reason to post it so that you can define that set.
Yeah, so I think our current thinking is to post possibly this time post everything up to and including the core patches that has to do with scheduling, leave out the stuff that has to do with IPA thermal integration, and leave out SCED-Freak because it's got its own life now. But in the future, we might not post a consolidated thing, we might just point in our postings and say this is part of, or we have an updated integration branch and we'll have a version number on linuxarm.org. Yep. So you will always be able to find it there. So if you don't post the full thing, there will be a link pointing to the integration branch where you can find the full story.
Okay, thank you.
You're welcome. No, that's all right.
So with energy management, we'll eventually hit a ceiling, the maximum we can do with our architecture. Do you have a feel about where we stand in terms of the ceiling for big.LITTLE architecture? I mean, there is a limit to maximum power optimization we can, or energy optimization we can do for our architecture. Do you have a feel that where we stand in terms of what maximum can be done versus what is currently implemented?
So your question is whether you think that this is as far as we can ever get in terms of energy optimizations
Yes.
in software, or if there is more to do. I think there will always be more to do. I mean, we're trying to address the bits where we think there is most impact right now. I mean, we have the big.LITTLE architecture, which has some features that you don't see anywhere else, and in terms of power and performance management, and we're trying to fix that first and get that properly supported. And there are a lot of things that we can optimize beyond that. I mean, Daniel is working on scheduler CPU idle integration. We're not sure where exactly that's heading yet, but there are possibilities for optimizing how you schedule tasks versus which power stage do you have on your system. And there's a whole lot of work going on in SCED-Freak about finding the best heuristic to try to give you the user experience you want, but saving power at the same time. It's really complex. So I think there are many areas where we can do improvements, and a lot of them we haven't addressed yet. So I definitely think there is more work to be done.
It's worth bearing in mind that so our focus is largely on the scheduling side, right? But all of this stuff, any existing strategy that evolves in Linux for energy conservative operation, there's lots of stuff going on, like SOC idling and improvements that will come because of GenPD and everything else, right? That just naturally complements this work. This just rides on top. So yeah, insofar as the AP side, application processor side optimizations go, this gives you a fair bit of a jump ahead. But there's lots more that will come from the rest of the system because of all the other work that's going on, right?
In fact, that was my follow-up question, is that a lot of things you can do on different, if you have a heterogeneous system, some things can be done on GPU and same thing can be done on CPU as well, with different performance figures, power or actual throughput figures. So does this, or do you have a plan to evolve this scheduling mechanism to figure out what to do on which core, other than the CPU core?
Not at present, no. I think I know where you're going with that one. Okay. You mean like special coprocessors, like GPU kind of workloads and all that, right? We haven't really gone in that direction just yet, I think. I mean, we have a few theories, but how applicable those theories are, it's kind of difficult to say. As in, if you have like a job pipeline that's interacting with a coprocessor of that sort, it's still going to have load connotations on the application processor. So in theory, the existing load tracking scheme should be able to deal with that. But there are other problems there to do with latency and kind of quality of service paradigms. And actually, some of the stuff we're doing over here, like SchedTune, can help with QoS. That's an interesting topic. Patrick will touch upon that in his session.
Yeah, thanks.
Just a quick question. I was just wondering how much off-list interaction you have with the maintainers, if there's much sort of back-channel discussion going on, if they're feeding you suggestions on things, or, what's going on there that's not on the lists?
Not a lot. I mean, I think we all hang out on the Linux RT-IRC channel, which seems to be Peter's preferred hangout place. And we do sometimes have off-list discussion with him, but I won't say it's extensive. I mean, if you have a quick question, I think the easier way is just to ping him there. I mean, I had discussion about the load balance code, for example, on RSC, and because I found a bit of code that I simply couldn't get my head around how it's supposed to work, and I asked him, and he said he didn't know how it worked either. It was before he became maintainer that code went in, so. That's true. There was another discussion about SCED-Freak. Somebody mentioned something, and I thought that couldn't just pass on without any comments, so we had a discussion there. Yuri was there as well. So I think it's a good idea to hang out on some of those channels.
So as a sort of a side question to that, I mean, do you think that Peter expects that these changes represent the future of, that this is kind of the energy, like the energy model, for example? Is there an expectation, do you think, from him that your work is the future? Or is it, do you think he sees it as sort of it's nebulous as to the future and it's a science project? Or, what sort of impression do you get working from him as to whether he, thinks that this is going in the right direction?
This topic came up at the LPC last year, right? And the impression we got is that Peter Zylstra has kind of bought into this because, so I was there from kind of a thermal perspective where we already use a model to drive thermal management. And he was like, oh, I didn't know you had a model there. You should use the one in the scheduler. I was like, yes, we are waiting for the scheduler model to get in to start using that. So that doesn't give you the impression that he's thinking it's kind of a nice idea, but I don't really see it going anywhere, right? Especially if he's kind of planning dependencies or suggesting dependencies on top of what's already happening. But that's my...
So I think you are right, and actually, yeah, I don't think Peter's opposed to the idea, and actually we can't take the full credit of having an energy model in the scheduler because I think it actually was. It first came up at a discussion at Kernel Summit in Chicago, I think, with Paul Turner in the room, and he said we should really have a model to describe how the platform works. So the idea actually came from Peter and Paul to begin with, and we just took it and turned it into a design, or at least a proposal for how it could be done. So I don't think it's against his vision. I'm not saying that this is the final solution. If somebody comes up with something which is much more brilliant and matches the requirements a lot better, then go with that. I mean, as far as I know, this is the only proposal for doing something like this, but ideas are welcome, of course. Yeah, on LKML. There are other solutions as well, but this is the only one I've seen posted on the list. There's another question here.
I get to know from some members, they said that maybe ARM will have a new CPU, for example, new architecture, so I'm not here. Do you have some discussing for the new CPU architecture? So do you think there have some change for the power modeling? Where impact for this part?
So I think it's probably better if that's addressed by our product management lobby. We do have insight into those, but A, we can't talk about it, and B, even if we did, we probably won't be as well informed as the product management guys are. So if you want some viewpoints from a partner perspective of what's happening with the roadmap, I'm sure somebody can answer that for you, but it's not us. Yeah, that's a very good point. As a general theme, the reason we've invested so much into EAS is because we see it as the strategically viable vehicle moving forwards for all of our processor roadmap, right? Yeah.
I mean that CPU maybe where to change, have the L1 cache and maybe have a L2 cache, such like this change, because maybe have different CPU cache, the hierarchy.
Yeah, I think that's just like detailing around specifics of the roadmap that is like confidential information, basically.
But I think what we can say is that we are aware of changes in the roadmap, and we do have that at the back of our head when we think about how to implement EAS. So we don't do things that will harm us later. More questions? I'm well over time here, so if you don't have any questions, I think we'll end here.
Maybe you can continue during the
So there is the hacking session at 2 with Puneet and the IPA discussion. So you can come along and ask more questions there, or please find me. I'm here all week. Thank you very much for listening.